So far, what we have seen is that we have seen serial execution. I need to talk slightly more in depth about this. So now we have seen the single cycle processor, but I did not tell you what's the drawback. The drawback is really the long clock cycle time. Okay, so remember that the single cycle CPU, it means that each instruction is going to complete in one cycle, in one clock cycle. So whether this instruction is an ALU or load or a store or a branch or a jump or even any other type like floating point, for example. But we did not really do floating point. So we just focus on these 5 types of instructions. So the main drawback is the long clock cycle time. This is the major drawback of the single cycle. Okay, so that's the long clock cycle time. So you have to increase the clock cycle, and by increasing the clock cycle, we are reducing the clock frequency and we are making the program to run slower. So we are increasing the execution time, and therefore we are reducing performance. Okay, it's very simple. So so what we are saying here is that if you are going to use a single cycle processor that we have implemented, we went into data path and control, we already have seen these details, right? So it means that if we are going to design the CPU like this, then it means that we are going to make all the instructions to take as much time as the slowest instruction that we have in the CPU. That's what it means. Okay. So for example, if you have an army of people that actually are marching, okay, and therefore you are going to actually to make all of them, okay, to run as slow as the slowest person in the army, then this is going to slow everyone, right? So the same thing here, if you actually have like, okay, billions of instructions in the program, and you are going to make all of them to run as slow as the slowest instruction. What does this mean? It means that all of them become slow, right? And this is going to increase the execution time, and it will have negative impact on performance. So now we can say that, okay, let us go slightly deeper into the details. If you take, for example, let us say an ALU instruction, first you need time to fetch it. So this is the instruction fetch time, because it takes some time. Now here I'm showing the time here for fetching the instruction, okay, from, let us say, the instruction memory or the instruction cache. I'll talk about caches later. Then you need some time to decode the instruction and to read its registers from the register file. Okay, this will take some time, right? Then you need time to execute the instruction on the ALU. And then you need some time to write the result back into the register file. So this is what needs to be done in the case of an ALU instruction. You need to do all of this within a single cycle, within one cycle. Now, in the case of a load instruction, now notice that every instruction needs to be actually fetched. So therefore, you can see that the instruction fetch is the same here for all instructions, because every instruction needs to be fetched. Okay, and then after that, every instruction needs to be decoded. And then you have to read the source registers from the register file. Now, in the case of a load instruction, we use the ALU to compute the address. You can see here address calculation. So rather than, so there is no here arithmetic operation, there is actually just a data transfer. Load means data transfer. So we use the ALU to do address calculation to compute the address in memory. And then we access the memory. So notice that there is a memory read, and this is going to take some time to read the data from the data memory, which is really in reality is nothing but a data cache in real CPUs. And then after that, after we have the data, we need to write it into the register file. So there is register write. So after we have read the data from the data memory, then we have to put this data, we have to write it in the register file. So notice that we have increased the delay, so the load will take longer, okay, to complete than an ALU instruction. So notice that how we have extended here the delay. That's the longest delay here, which is for a load. Okay, it takes longer than the ALU. In the case of the store, we fetch, we decode, we compute the address, and we write the data in memory. Now, there is no register write, so therefore it takes slightly less time in the case of the store instruction than in the load. In the case of a branch, it takes even less time because all I have to do is that fetch the instruction. So that's the instruction fetch. And then we read here, okay, so we read the registers because we have to compare two registers. So branch is equal, branch not equal. So we have two source registers, RS and RT. So we have to read them from the register file. So once we have read the data from the register file, okay, the next step is to compare and update the PC. So we compare them. So we use the ALU for making a comparison. Okay, so we use the ALU to make the comparison. Okay, so we do a subtraction, and then we can check if the result of the subtraction is 0 or not 0. Okay, and then we, after doing the subtraction, we can actually update the PC. That's it. So all the branch does is just update the PC, because once we have updated the PC, we are done. Okay, we have branched, or we don't branch, and we just go to the next instruction. So notice that in the case when we are reading the data from the register file, I can also calculate the branch target address. Okay, because I already have the immediate inside my branch instruction, which is PC relative addressing. So we can just use an adder to calculate the branch target address. So even before knowing, okay, what is the outcome of the branch, taken or not taken, because we have two outcomes, we can actually just calculate the branch target address, and then we use the ALU to know what's the outcome, and then update the PC, and we are done. Notice that there is no addressing, there is no access here to the data memory, and there is no register write. That's in the case of a branch. So the branch can be executed in less time. So it takes less time to complete than the store or the load instruction. Now notice that in the case of the jump here, that's even actually faster. Why? Because all what we need to do is that just fetch the instruction, decode it. So when you decode the instruction, okay, when you decode the instruction, you know from the opcode it's a jump. So all what we have to do is just update the PC and we are done. There is no need to read any register. There is no need actually to use the ALU. There is no need actually to access data memory. So it takes less time. So now you can see that different instructions have different delays. On the data path, they have different delays, but we have to choose our clock cycle. Now we cannot really make the clock cycle very short, because if you make it very short, then the load instruction, those that will take longer, okay, to complete, they did not really finish yet. Okay, so this is why in the case of the single cycle processor, we choose the clock cycle to be as long as the longest instruction that has the longest delay, which is the slowest instruction, that has the longest delay in my instruction set. Now, this is not good. This is the drawback. That's a drawback, okay, of the single cycle processor. Now, I have an example about this, but before I show you my example, can we do better than this? Can we do better than this?
Of course, there is a way to do it better.
Okay, how? You tell me.
I don't have an idea.
If anyone has a clue how actually you can design a better CPU than this?
Doctor, we cannot change the clock cycle, right?
No. The clock cycle actually is fixed. So you have a clock generator that's going to generate the clock cycle. But in the case of the single cycle, you have to choose the clock cycle to be long, okay, long enough to take into account the longest delay of any instruction that you have in the instruction set. And that's the major drawback of the single cycle processor. So how can we do better? Of course, you cannot actually change the cycle from one instruction to another. This is never done. Nobody actually does this. Nobody changes the clock cycle from reduce the cycle or increase the instruction by instruction, because you have to decode the instruction, okay, to see that actually what is the nature of this, okay, and you cannot actually do this cycle by cycle. So nobody does it this way. So how can we design a better CPU, a faster CPU? Yes?
For example, ALU and load and store, branch, jump, they are common. I mean, why we can just one cycle we fetch the instructions, for example. Can we?
Can we
in
what?
one cycle? I mean, in one cycle, we do it for all instruction fetch, in ALU, load, store, branch, jump, because
so we
they have
use
the
actually,
first step. They are the same first step.
okay,
I
so
mean,
the first step is the same. Instruction fetch is the same, right?
Yeah. Yes. So can we do it for all? I mean, for the 1 o'clock, we can
do what?
push
Do what?
instruction fetch.
Yeah, we do what? We do it. How we do it? يعني, can you explain to me? Slightly يعني better يعني. Can you explain to me?
يعني هو ال ALU واللود مثلا راح يحتاجون two inputs, for example, or one input. So we push the inputs for the all parts of the CPU, for example, store, in one cycle, rather than we every time we go through ALU, we push an instruction.
Right. Let me try to understand what you are saying and try to explain it in a different way. Okay. Let me try to explain it. So rather than doing all of this in one cycle, let us try to break down the execution of a single instruction, of one instruction, into multiple cycles. Let me repeat this. Rather than having a single cycle processor, let us redesign the processor to be multi-cycle. Now, the idea here is to reduce the clock cycle, but every instruction will have a different number of clock cycles. Is this clear? So what you are trying, what I try to understand from you is that you want to fetch the instruction. So every instruction has to be fetched. So we try to fetch the instruction in one cycle.
Yes.
We try to decode the instruction and read from the register file in another clock cycle.
Yes.
We try to use the ALU in a third clock cycle. So now the number of clock cycles, we try to access the data memory in a fourth clock cycle. And now we try to write back the register file in a fifth cycle. So therefore, the number of clock cycles is going to vary from one instruction to another. That's really the idea. Okay. Let me talk about this idea. This is called the multi-cycle implementation. Yani we can implement the data path and the control. We can do it in a way that each instruction will take multiple cycles. So we break the instruction execution into 5 steps. 5 steps, as indicated in the previous slide. The first step is called the instruction fetch. So we try to do it in one cycle. Now, of course, it takes less time. Okay, we can reduce the clock cycle here, right? Just to fetch the instruction. Okay, that will be done in one cycle. In the next cycle, we decode the instruction. Okay, this is called instruction decode. We read from the register file. We can do these two things in parallel, by the way. They are not related. Yani while you are decoding, generating the control signals, you can read 2 registers from the register file anyways. Okay, just read them. Even whether you need them or you don't need them, just read 2 registers. Okay, so these 2 things can be done at the same time in parallel. And then we can generate the target address for a jump and branch. Okay, even without determining the control signals, generate, okay, the address. Okay, this will be the target address, okay, for a branch, for a jump. Whether we are jumping or branching or not, calculate the jump address, calculate the branch target address, the jump target address. Right. So this can be done in one cycle. You don't really have to, okay, so you fetch in one cycle. In the next cycle, you do the decode, read from the register file, and can calculate the target addresses, okay, in the second cycle. Now you execute in the third cycle. You can use the ALU for execution. You can do it. You can use the ALU for memory address calculation, or you can use the ALU to determine the outcome of the branch. In the case of the branch taken or not taken, okay, equal or branch equal, branch not equal. So we have different branch instructions. In the fourth cycle, you can use it actually for memory access. Now that's in the case of load and store. If you have load or you have store, you need to access the data memory. Okay, in the case of the fourth cycle, you can also use it to complete an ALU instruction. And if it's not loaded, if it's not stored, if it was an ALU, write back the result into the register file. Okay, so that actually can be done in the fourth step. Now, in the case of the fifth step, one needed actually for the load instruction to complete. That's when you would like to write back the data into the data that was read from the data memory. You would like to write it back into the register file. So you can see that the number of clock cycles can vary, okay, from one instruction to another. And this is why it's called a multi-cycle implementation. That's the meaning of multi-cycle implementation. So as we have seen here, okay, from this previous slide, if I have a jump, I can do it in 2 cycles. If I have a branch, I can do it in 3 cycles. If I have a store, I can do it in 4 cycles. The same thing in the case of ALU, I can do it in 4 cycles. And in the case of a load, I need 5 cycles. So the load will have the longest delay because it requires 5 cycles. So now I can actually have a table, which is shown here in the case of the multi-cycle implementation. So we can say that ALU and store will take 4 cycles. That's for ALU and for store. For a branch, I can do it in 3. For load, I need 5 cycles. And for jump, I need 2 cycles. So these are my 5 different classes of instructions. Okay, we have load, we have store, we have ALU, we have jump, and we have branch. Okay. So that will be my focus, inshallah, in my next lecture. I'll talk about the multi-cycle implementation. I will give you an example in which we can compare the performance of single cycle versus multi-cycle. I have an interesting example about this. And then I will introduce pipelining. Okay, what's the meaning of pipelining and how we can even improve performance beyond the multi-cycle. Okay, so I will talk about this, and I will talk about the performance of the pipeline before we start and dig deeper into the data path and control for a pipeline CPU. So that's it for today. Do you have any question?
Doctor, I have a question.
Yes, further.
Isn't it the same when we say ALU and store has a 4 cycle? Is it the same as CPI equal to 4?
Yes, CPI for this class will be equal to 4. Yes.
Yeah, okay.
Because we have actually 4 cycles per instruction. Okay, yes, correct. And I'm going to actually show you an example about this, inshallah, in my next lecture. So wait until Thursday. We will see actually a very interesting example about actually the multi-cycle implementation and how we can compare the performance of multi-cycle versus single cycle, and hopefully we can improve performance, okay, and reduce the execution time. So as shown here in this slide, we can do the instruction fetch in 1 cycle. So that can be done in 1 cycle. I can decode the instruction and read from the register file in a 2nd cycle. I can execute the instruction on the ALU or compute the memory address in the case of load store, or doing, for example, a comparison. Okay, in the case of a branch, we can compare, okay, if they are equal or not equal. So we can do all of this in a 3rd cycle, and then we can either access the data memory in the case of load and store, or we can write back to the register file in the case of an ALU. So this can be done in the 4th cycle, and then the 5th cycle, in the case of a load, we need 1 more cycle, okay, to write back, okay, the data that was loaded from the data memory into the register file. So you see that here the number of clock cycles per instruction can vary. It can vary from 1 instruction to another. And for this reason, I have this table here that shows the number of clock cycles per instruction. So that's the CPI, okay, per instruction. So I have the CPI for the ALU, for the store. I have the CPI for the load, for the branch, for the jump. So notice that the number of clock cycles can vary from 1 instruction to another according to our design. Of course, it can be more than that, depending, of course, on the implementation of the CPU. Sometimes you have instructions that can take more than 5 clock cycles. Okay, and for example, if you have floating point instructions or complex instructions like division, they might take even more clock cycles. But typically, the frequency of these instructions in the program might be small, and therefore might not really impact too much the overall execution time of the program. Okay, so that's really the idea of the multi-cycle implementation. Of course, we have to go back and change the implementation of the data path and the control, but I will not do it for the multi-cycle. I just would like to make a comparison, okay? So the idea is to compare the performance of the multi-cycle versus the single cycle, okay, assuming that we have this table here that shows the number of cycles per instruction, okay, for these 5 different classes of instructions. So we have ALU, we have load, we have store, we have a branch, and we have a jump. Notice that for the ALU and for the store, the number of clock cycles is the same. They need not be the same. I'm assuming them to be the same, okay, in the case of our design. But you can notice that here in the case of store, you finish after writing the data memory. In the case of the ALU, you finish after writing the register file. And I'm assuming that these two will take exactly 1 cycle, even though register write might take less than memory write. If memory write is too long, we might also break it down into 2 clock cycles. So it all depends on the design of the data path and the delays in the data path. Right. So now the question is, let us take a look at this example. Okay, so I'm going to assume the following operation times for the components. So we're going to look at the components inside the CPU. So in the case of the instruction and data memories, we're going to assume that the access time, that's a delay. So the delay in the case of the instruction memory and the data memory will be 200 picoseconds. Okay, so this is given to us. Sometimes we might actually have slower memories. Okay, so here I'm assuming very fast memory in which we can access the instruction memory in 200 picoseconds. Similarly, we can access the data memory in 200 picoseconds. Now, the delay in the ALU and the adders, it will be 180 picoseconds. Now, the ALU for executing the ALU instructions, and the adder here, for example, for incrementing the PC or for calculating the branch target address. So this is the same, which is 180 picoseconds. Also, we have the delay in the decoded stage. Okay, so that will be the logic, okay, the control logic for decoding the instruction, as well as the register file access. Okay, so whether you would like to read from the register file or you would like to write to the register file, this will be 150 picoseconds. So this can be actually quantified, okay, by the designer of the components. So when you have a register file, the question is, how long does it take to read from the register file? What's the delay in the register file? How long does it take to write, okay, into the register file? There is a setup time, right? So these delays are very important when we would like to look into the performance, okay, of the single cycle CPU, and I would like to compare it against the performance of the multi-cycle. I'm going to ignore the delay in the program counter register. Usually in every register, there is a small delay to change its output after the edge of the clock cycle. Okay, there are multiplexers. There is an extender, which is very simple. There are wires. Even wires, they have delays. So I'm going to ignore these delays. Now, these numbers are just chosen randomly, okay, even though they might not be realistic, okay? So sometimes we have to look at the existing technology and we have to see the real delays, okay, in these components, okay? Then we can actually have, more accurate results, okay? So I'm just choosing these numbers, okay, in this example. But in reality, we have to take into account everything. And even in the case of a multiplexer, we have to look at the delay inside the multiplexer. Even the wires, okay, people take the wires because they are dealing here with a very fast clocks, okay, and therefore the wire delay becomes important. Okay, so as the wires become smaller and thinner, okay, then they will have higher resistance and it will take capacitance. And therefore, it will take longer for a signal to propagate through these wires, and the wire delay becomes important. And even the wire itself, there is a delay in the wire. So the signal does not really propagate instantaneously inside the wire. It takes time for the signal, even though this time actually is small, but it is taken into account by circuit designers. So if you would like to go to the low level, okay, circuit implementation, and take into account all of these delays, then we have to do that to get a good approximation of the delay. Now, the question is, assume that we have these numbers, okay? So the question is, which of the following would be faster? Should we use the single cycle implementation for all instructions, or should we use the multi-cycle implementation, which is optimized for every class of instructions, as we have seen in the previous slide? This is the question. Now, in the case of the multi-cycle, as we have seen that different instructions will take different number of clock cycles. And in order to answer this question, we are going to assume the following instruction mix. I'm going to assume that 40% of my instructions are ALU, 20% are load, 10% are store, 20% are branch, and 10% are jumps. Now, why do I need this instruction mix? Why do I need this instruction mix?
To calculate the average CPI, which is a weighted sum.
But do I need this actually for the single cycle? Yeah, we need this. Yes, we need. We need it for what? The single cycle or the multi-cycle?
Multi-cycle.
Exactly. We need it for the multi-cycle. Now, for the single cycle, what's the CPI?
It is one. It doesn't matter.
Yes.
Yeah. So it is one for all instructions. So it is one because we are designing the data path, okay, to take one cycle per instruction for all instructions. But in the case of the multi-cycle, we are redesigning the data path. So how do I implement the data path in the case of the multi-cycle? Any idea? What changes are needed to implement the multi-cycle? Yani you as a designer, if I give you this problem, okay, in the lab, and I tell you, okay, you have a single cycle implementation. I really would like to get a multi-cycle implementation. What changes you have to make in the data path and the control to implement a multi-cycle implementation? How do you do this? I will not go into the details, but the question is, if you want to have a multi-cycle implementation, how do you do a multi-cycle implementation of the CPU? What changes are needed? Already we have seen the single cycle. Yes, Khalid, Fadal.
I think we need to add a clock to the control unit.
Well, we don't really add the control to the combinational circuits. We add the clock to the memory elements, to the registers. Of course, we need to have a clock. Already we have the clock in the case of the single cycle. Already the clock is connected to the PC register. Also, it's connected to the register file. Also, we have also connected the clock to the data memory in the case of the store instruction, so that we can synchronize the writing, the store operation, okay, in the data memory. Also, we can synchronize the write back into the register file and also the update of the PC register. So what changes are needed for the multi-cycle? Anyone?
Use more than one clock.
Sorry, Ali, I did not understand your answer. I did not hear it properly.
Use more than one clock instead of one clock for every.
No, you only need one clock inside the CPU. You don't need multiple clocks. What is missing? Yani after I fetch an instruction, where do I put this instruction? When you fetch an instruction,
memory.
You need a register. You need a register. Okay, an instruction register to store the instruction that was fetched. In the case of the single cycle, we did not really use registers, okay, to store the instruction itself. We connected them with wires. So now what we need to do is that we need actually, after the instruction memory, I need a register to store the instruction itself. So therefore, you need to do this in one cycle. Just you need an extra register after the instruction memory to store the instruction. Like in the case of after computing the result of an ALU, where do you place this ALU result? You also need the register. You need also register. So therefore, you start having to add registers into the data path Okay, so these registers are needed actually for the intermediate results. Okay, and for example, when you compute the ALU result, before you write it back, you have to put it in a register. So therefore, by introducing registers, you can do the instruction, okay, in multiple cycles. So you can break it down into multi-cycles. And therefore, at every step, you can actually put the result in a register. So what is missing are registers, okay? But these registers are internal registers inside the CPU, okay? And then finally, once you have the computed the final result, you can write it back into the register file. So you need a register for the instruction. After the instruction memory, this is where you place the instruction. You need maybe registers at the inputs of the ALU. After you have read from the register file before you execute. After you execute, you need a register after the ALU. After you load the data from the data memory, you need also a register to put the data. And then finally, you can write back the result into the register file. So notice that we have introduced additional registers in the data path. And the reason is that we need to have these registers to store whatever we have before we move to the next cycle. In the case of the single cycle, we did everything in one cycle. But now we are breaking it down into multiple cycles. So there are changes in the circuit, in the data path. Okay? Also in the control, there are also changes. Right. So now how do I solve this problem? How do I compare the single cycle with the multi-cycle? So how do I solve this problem? I really need to compare single cycle with the multi-cycle implementation. So how do I do this comparison?
Execution time.
Yes,
The same equation we use.
So we have to go back to the CPU execution time. Yes, thank you. Now we don't know exactly what, yeah, so what do we need to calculate?
We already have the CPI.
Yes, but we know the CPI for the single cycle. We need to calculate the CPI for what? For the multi-cycle, right?
Yes. For
yes.
each class.
Okay. Yes. So we need to calculate the average CPI for all of them. We already have the CPI for each class. Already we have seen it in the previous slide. But what I really care about is really, I have this table here that shows the CPI for each class of instructions. I need to calculate the average CPI. So this is why we have this instruction mix here, which is given to us so that we can calculate the average CPI for the entire code. Right. What else is needed?
CPU cycles.
Yes. Is the cycle time is the same for the single cycle or the multi-cycle? Is it the same or different?
It is different. Yeah,
so
for one cycle, it is the same.
Yeah, so so which one has a better clock cycle?
Of course, the single cycle will have a longer
yes,
cycle time.
Yes, so the single cycle will have a longer cycle time. So how do I calculate the clock cycle for the single cycle and for the multi-cycle implementation? So how do I calculate this clock period? What shall I do?
For the single cycle, we should consider all instruction classes, and we take the longest delay. But in the multi-cycle, we take the longest delay in one. I mean, we check the class instruction, the longest delay in a single class instruction. Like here, 200 picosecond for instruction for access time to data memory.
Excellent, excellent. Right. Okay, so let us do this. Let me explain it, what you said. Okay, let me explain it to the other students. So now what we need to do is that we need to construct a table, okay, and show all the delays in the instruction memory, the register file, the ALU operation, the data memory, and the register write. Right. So in the case of the instruction memory, I'm assuming that it takes 200 picoseconds to read from the instruction memory. I'm assuming that the instruction memory is small and it can be accessed very quickly, very fast. Sometimes if you have a larger memory, it will take longer to access. Anyways, these are the numbers which are given to us in this problem statement. So it will take 200 picoseconds to access the instruction memory. Then it takes 150 picoseconds to read the data from the register file. Then it's going to take 180. I'm going to say that, okay, for the control logic, remember that in the data path, we have, inside the CPU, we have data path and we have control, right? So while we are reading from the register file, we're reading two registers, by the way, okay, we can decode the instruction and generate all the control signals. Now you say, why you did not really add the delay inside the control logic? This is a very valid question, by the way, because the control exists, right, inside the CPU. Now, the reason why I did not really add it is that because my assumption is that I'm decoding and I'm accessing the register file at the same time in parallel. Remember that inside the CPU, once you have fetched the instruction from the instruction memory, you have the opcode. So inside the instruction, you have the opcode. So that opcode can be decoded. You can generate. Also, you have the function. In the case of the ALU R type, we have the function code. So you can actually decode the instruction. You can generate all the control signals, and at the same time, you can read from the register file. You can read the value of register RS and RT. Correct? So we can do these two things in parallel at the same time. So for this reason, we have to say which one takes longer. Is it the control logic or is it the register file? Here, I'm assuming that the register file will take longer, and therefore, in the 150 picoseconds, already we have decoded the instruction. We have generated the control signals. So these two things can be done in parallel, and I'm assuming that we can decode and generate all the control signals within this 150 picoseconds. Now, there is also, if you remember that we also had the multiplexer to select whether it's actually RT or RD is my destination. I'm ignoring this delay, or I'm assuming that we can also overlap it, okay? It means that we can do it, all of this can be done within the 150 picosecond, okay? Next, after we have read the two registers from the register file, then we execute. And the assumption is that it takes 180 picoseconds on the ALU. Now, you might say that, well, it depends on the instruction, which is true, yes. So the delay in the ALU can vary from one instruction to another instruction. Yeah, for example, if you have an addition and you have a slow ripple carry adder, that might increase the delay inside the ALU to compute all the bits, okay, for the sum. If you are adding, or let's say subtraction, you can do it addition to the 2's complement. Okay, so now you look inside the ALU and you look at the longest delay. So now what we do is that here we take, okay, the longest delay inside the ALU. Remember that the ALU is a combinational circuit. You provide the input, you get the output, there is no memory inside the ALU. So we go by the longest delay inside the ALU, and this is the 180 picoseconds. So if you have a logic operation like AND, OR, and so on, they can be done within 180. In fact, they might take less than 180 because we can do all the bit endings, so it's bitwise. We can do it in parallel, and therefore we can get the result much faster. But we always go by the longest delay inside the combinational circuit. So for example, if addition and subtraction takes longer, okay, than the logic operation, then we focus on the longest delay. And even for addition and subtraction, we have to look to say that maybe I'm going to produce the sum bits in different delays. Yani we have 32 bits, okay, in my result. But the most significant bit will take longer to produce than the least significant bit. So we go by the longest delay, yani the most significant bit. This is basically circuit analysis. This is basically how you analyze the delays inside the circuit. Is this clear? So when I put here just a single number, it does not really mean that actually all the bits are going to be produced at the same time. No, some bits will be produced even before 180 picoseconds, but we go by the longest delay. Right. Now, in the case of ALU, there is no memory access. Notice that this is, I left it blank here. And there is register write that's going to take 150 picoseconds because it takes time to decode the destination register and also to write the destination register. Okay, so that's 150 picosecond, which is assumed here in this example. Now, if you add these numbers here inside this row, okay, the total is 680 picoseconds. And from the time you have fetched the instruction, you present the address in the PC, until you get the result written back into the register file, that will take 680 picoseconds. Now, notice that there are multiplexers. Yani, for example, there is a multiplexer, okay, at the end, okay, before you write back, okay, so to select whether the ALU result or the data which is loaded from the memory should be written back into the register file. There is a delay inside the PC register to actually to update the so from the edge of the clock until you get the address, okay, at the output of the PC register, there is a small delay. So we are ignoring these delays, or we can just add them up, okay, in these numbers. And we are lumping it in these numbers. Right. So so that's for ALU. If I would like to do it for load, you can see that I have to also to add to it here the data memory access, and this is going to increase it to 880 picoseconds. In the case of store, we finish after writing to the data memory. There is no register write, so this is going to make it 730 picoseconds. So notice that the total delay can vary, okay, from one instruction to another. In the case of a branch, we execute the branch. We need to make a comparison because it's a compare and branch. So we compare and then we update the PC. Okay, I'm assuming it also to be 180. In fact, it will take slightly longer, okay, to update the PC because you need to use the PC logic after you have detected if they are equal or not equal. Then there is a small PC logic, okay, control logic, which is for updating the PC, okay, that will select, okay, the branch target address. Now notice that the branch target address can be calculated early because there's an adder, okay, so this can be done in parallel. So while we are comparing, already we have calculated the branch target address, so we don't really add the delay for calculating the branch target address because there is an adder that will calculate the branch target address. I'm ignoring this delay for a purpose because you see that we can do it in parallel, okay, while we are computing here while we are comparing the values of two registers, we have already calculated, okay, the branch target address. Finally, in the case of a jump, there is no need to do any kind of execution on the ALU. I just actually fetched, okay, there is no need to read from the register file. All what we need to do just decode. Notice that the opcode equal to jump and update the PC register, and we are done. So therefore, you can see that the total delay is also less, 350 picoseconds. Is this clear? This is the importance of this table, is that we have analyzed, okay, the total execution time, not execution, the total time actually for one instruction. So this includes fetching, reading from the register file, executing, accessing the data memory, and writing back the result into the register file. So that's the total time. This is the total latency of one instruction from the time you fetch until you complete it. Okay. Notice that actually how it varies, okay, from one class to another. So now the question is, what should be the cycle time? This is my question to you. What's the cycle time for the single cycle data path? What's the clock cycle?
880.
Yes. So we have to go by what? The slowest instruction. The slowest instruction. So the slowest instruction has the longest delay, which is 880 picoseconds. Okay. So that's 880 picoseconds. So this must be here the clock cycle, which is 880 picoseconds, which is determined by the longest delay. As the minimum, it has to be 880 picoseconds. Of course, you have to also have some kind of small margin to determine. Maybe you would choose, for example, 900 or 1000 picoseconds, okay, as a circuit designer. You cannot actually go below 880 picoseconds because you have to look at the longest delay. You have to ensure that the data has been loaded and written back into the register file before you can actually update the PC and start fetching the next instruction in memory. So as a minimum, you need 880 picoseconds according to this table. Okay, is this clear? That's the clock cycle for the single cycle data path. Now, for the multi-cycle implementation, what do you think? What do you think the clock cycle will be for the multi-cycle implementation? Please quickly, so that we don't waste much time.
200.
How did you determine this?
Because the longest instruction class the longest instruction step takes 200 picosecond. So we have to follow this. We cannot use 150 because it will be shorter. Some instruction will take more. Some steps will take more than 150.
Yes. So therefore, when you break down, okay, the steps of an instruction into, so therefore, in the case of the multi-cycle, we fetch in one cycle. We decode the instruction and read from the register file in another clock cycle. This is why I said that we have to have internal registers inside the CPU. These are different from the general purpose. These are needed actually to put the instruction, to save the instruction for the next cycle. And also after we have read the data from the register file, we need actually to save the values of the registers before we execute. We need to save them in registers, in internal registers. After we have executed, we need also a register. So therefore, it takes multiple cycles, okay, for an instruction to execute. So now we can reduce the clock cycle time. I don't need 880 picoseconds, okay, like in the case of the single cycle. I can reduce it here. So we see here that in one step you can do it in 200, another step you can do it in 150. So you have to look here at the longest delay at any step. Okay, that's what Amr is trying to explain to us. Okay, so here we can say that what's the maximum of 200, 150, and 180? We have to fix the clock cycle. So we choose here the maximum delay at any step, which is the 200 picoseconds. Again, you may actually choose slightly higher than 200 so that you can actually have a small margin. But you can guarantee that in 200 picoseconds, you can do any one of these 5 steps, okay? You can guarantee that. Right, so now you can see that for the multi-cycle implementation, we have improved a lot the clock cycle. So rather than using a clock cycle, which is 880 picoseconds, we are using a clock cycle, which is 200 picoseconds. By the way, 200 picoseconds means what's the clock frequency? If we use 200 picoseconds for the clock cycle time, what will be the clock frequency?
1 over the clock cycle.
Yeah, give me a number. I know that.
5.
What is that? 5 gigahertz. Yes, 5 gigahertz. That will be very fast clock frequency. By the way, 200 picoseconds is a very short amount of time. Okay. Yani, so many things can happen. Okay. Yani, if you compare, so 200 picoseconds means 5 gigahertz as a clock frequency. This is actually probably one of the fastest CPUs that we have today. Okay, 5 gigahertz. Okay, so basically, if 5 gigahertz means that 5 billion cycles per second. So basically, the clock is repeating 5 billion times. Okay, and if you can actually living in a world in which the cycle is, if you can feel this cycle, like you feel this second, then if you feel the cycle and you have 5 billion cycles per second, 5 billion cycles, that would be a long, long time to be, okay? So if you are living inside the computer and you are yourself, okay, the second for you, the cycle is like the second for you, for us here as a human beings. And human beings, we are so slow with respect to computers that actually work at 5 gigahertz, okay, 5 billion cycles per second. We look very slow. Yeah, inside the computer, okay, just compare yourself. If you are very, very tiny and you are living inside these circuits and you can feel the clock cycle, okay, so the cycle for you is like a second for us, okay, then you will feel the 5 billion cycles like years. Okay, let me just use this simple calculator just to tell you how you can compare the 200 picoseconds or the 5 billion cycles per second, okay, with a second for us. Yani if I just change the time, okay, and I say that, okay, I'm going to make my time as one cycle as 200 picoseconds. What will be the second for the 200 picoseconds? It's 5 billion times, right? So if I would like to say, okay, what's the 5 billion times if you multiply 5 billions by 1 second? How many years it will be? You understand?
Yes. Yeah.
Okay. So use a small calculator here. Okay. So maybe, okay, I'll come back to this maybe. Okay. So it's not really important, but that's actually what, okay, I'll do this. This will be actually a small thing. But let us just finish this example here, the solution. So we got the clock cycle, which is 200 picoseconds. Okay. So what is next? We need to calculate what? What is missing?
CPI.
Yes.
Average.
Yes. So we need to calculate the average CPI for the multi-cycle. Now, for the single cycle, we know it's 1. For the average CPI, for the multi-cycle, now that's actually is the catch. We're trying to reduce the clock cycle. So we made the clock cycle actually much shorter, okay, or the clock frequency much higher to improve the performance. But this is what we gained. We reduced the clock cycle. But the catch is that the average CPI has increased. So now the average CPI, we said that 40% are ALU. So now it will take 4 cycles for the ALU. It's longer one cycle, it's 4 cycles. And then it will take here 5 cycles for the load. We said that 20% are load, 10% are store, 4 cycles for the store. Okay, 20% are branch, 3 cycles for the branch, and 10 cycles for the jump. So 2 cycles for the jump. So we got an average CPI, which is 3.8. That's the average CPI. So notice that the CPI has went up from 1 to 3.8. Why? Because we reduced the clock cycle and we are using a multi-cycle implementation. Right. So now, which one is better? The single cycle or the multi-cycle, and by how much? How faster it is?
We can calculate it. How,
yeah, we take the same
faster.
program. We take the same program. Yes. How do you calculate this, Ali?
We can compare the for the fixed cycle, which is 880 picosecond,
Yes.
divided by the new value of the multi-cycle, which is 200 picoseconds. Multiply. Multiply it by the sum of which is the average CPI,
which is 3.8.
Yes.
Okay, so what we need to do is that we need to multiply this 200 picoseconds by 3.8. Here you need to multiply this 880 picoseconds by the average CPI, which is 1 actually for all instructions. So it will be, if you would like to look here at the average time, okay, for one instruction, in the case of the single cycle, it will be 880 multiplied by 1 cycle, by 1, because the CPI is 1 cycle per instruction, right? In the case of the multi-cycle, it will be 200 picoseconds multiplied by the average CPI. So if I would like to calculate the CPU execution time, the instruction count is the same. So it's the instruction count multiplied by the average CPI multiplied by the cycle time. That was the performance equation, right? So let us do it for the single cycle. It will be the instruction count multiplied by 1, that's the average CPI, multiplied by the 880 picoseconds. In the case of the multi-cycle implementation, it will be the instruction count, the same instruction count, because what executing is exactly the same instructions, okay, multiplied by the average CPI, which is 3.8, multiplied by 200 picoseconds, okay? Now, this will give you, if you ignore the instruction count, do it per instruction, you will get 200 picoseconds multiplied by 3.8. So now when you divide the execution time by the execution time, get the speed up. So the speed up will be 880 multiplied by 1 divided by 3.8 multiplied by 200 picoseconds. So notice that here 3.8 multiplied by 200 is 760 picoseconds. So that's the average time per instruction. That's the average time per instruction. So 760 is better than 880, it's less. So therefore you get the speed up is equal to 1.16. So that's the speed up that we gain from the multi-cycle implementation. Okay. Any question about this?
So the speed up.
So we gain some speed up. Yes.
Which is 16% or.
Yeah, we can say that. Yes, 1.16. It means that 16% actually faster. Okay. or we multiply by 1.16. Okay, so the performance here is 1.16, or we are reducing the execution time, okay, by this factor.